Hello and welcome to a screencast introducing limit notation to describe long-range behavior. One of the important skills to develop in preparation for calculus is familiarity with the long-range behaviors of a library of basic functions and using limit notation to describe the long-range behavior. When observing a pattern in the values of a function that correspond to letting the inputs increase or decrease without bound, we are considering an infinite collection of inputs that are themselves following a pattern, and we ask the question, how can we expect the function's output to behave if we continue? For instance, we have regularly observed that as x increases without bound, e to the x increases without bound, which means that by allowing x to get bigger and bigger without bound, we can make e to the x also get bigger and bigger. Similarly, we've observed that as x increases without bound, e raised to the negative x tends toward 0, which means that by allowing x to get bigger and bigger without bound, we can make e raised to the negative x get as close to 0 as we'd like, without e to the negative x ever equaling 0, since e to the negative x is always positive. And we've observed that as x increases without bound, the natural log of x also increases without bound. Here we will introduce formal limit notation in order to be able to express these patterns even more succinctly. Let L be a real number and f be a function. If we can make the value of f of t as close to L as we want by letting t increase without bound, we write and say the limit of f of t as t increases without bound is L. If the value of f of t increases without bound as t increases without bound, we instead write the limit of f of t as t increases without bound equals infinity. Let's look at a few examples to better understand this notation. In all of these examples, we will use limit notation to describe the long-range behavior of the function. That is, we will use limit notation to describe how the function behaves as the input increases without bound. First, we have f of x equals e raised to the x. We already know as x increases without bound, e raised to the x increases without bound. And we can describe this long-range behavior by writing the limit of e to the x as x increases without bound equals infinity. Next, let's look at g of x equals e raised to the negative x. We know that as x increases without bound, e raised to the negative x tends toward 0. So this is an example where we can make the value of e raised to the negative x as close to 0 as we want by letting x increase without bound. We can describe this long-range behavior by writing the limit of e raised to the negative x as x increases without bound equals 0. Next, we have q of x equals 2 minus 3e raised to the negative x. We know that this is e raised to the negative x after a vertical stretch of 3, a reflection over the x-axis, and then a shift up 2. As a result, we know that as x increases without bound, 2 minus 3e raised to the negative x will tend towards 2. This means we can make q of x as close to the value 2 as we want by letting x increase without bound. In limit notation, we would have the limit of 2 minus 3e to the negative x as x increases without bound equals 2. Lastly, we have r of x equals negative x squared, and we notice that as x increases without bound, negative x squared decreases without bound. We can write this as the limit of negative x squared as x increases without bound equals negative infinity. In these four examples, as x increased without bound, the function either increased without bound, approached a specific value, L, or decreased without bound. What about when a function demonstrates none of these behaviors? For example, consider the sine graph. As t increases without bound, the outputs oscillate between -1 and 1, but never get closer and closer to a single value. nor do the outputs increase or decrease without bound. So in this case, we would say f does not have a limit as t increases without bound. So again, if f does not increase without bound, does not decrease without bound, and does not approach a single value L as t increases without bound, then we say that f does not have a limit as t increases without bound. Up to this point, we've focused only on the long-range behavior as x increases without bound. That is, we've only focused on the right end of the graphs. We can use limit notation and related natural ways to express the long-range behavior of the left end of a graph too. When considering the long-range behavior of the left end of a graph, we are interested in the behavior of the graph as x decreases without bound. And we can write x tends towards negative infinity when we want to let x decrease without bound. Let's look at a few examples. First, we have f of x equals e to the x again. We notice as x decreases without bound, e to the x tends toward 0. We can describe this long-range behavior in limit notation as the limit of e to the x as x tends toward negative infinity equals 0. Next we have g of x equals e raised to the negative x again, and we see that as x decreases without bound, e to the negative x increases without bound. We can describe this long-range behavior by writing the limit of e raised to the negative x as x decreases without bound equals infinity. Next we have q of x equals 2 minus 3e to the negative x. We observe that as x decreases without bound, 2 minus 3e raised to the negative x also decreases without bound. So in limit notation, the limit of 2 minus 3e to the negative x as x decreases without bound equals negative infinity. Lastly, we have r of x equals negative x squared, and we notice that as x decreases without bound, negative x squared decreases without bound. In limit notation, the limit of negative x squared as x decreases without bound equals negative infinity. Finally, if the limit of f of x as x approaches infinity equals a single value L, or the limit of f of x as x decreases without bound equals a single value L, then f has a horizontal asymptote at y equals L. So for example, the limit of e to the x as x decreased without bound equaled 0. So we could say e to the x has a horizontal asymptote of y equals 0. And since the limit of 2 minus 3e raised to the negative x as x increased without bound equaled 2, we can say that q of x has a horizontal asymptote of y equals 2.